Hello, everyone. We'll get started in just a moment once everyone has joined the room. If you've just joined, welcome, everyone. We'll get started in just a moment, waiting for everyone to join the room. And a quick test in the meantime. Can you hear me okay here at Harvard? Yes? Okay, wonderful. Good to see so many faces again. All right, we'll get started momentarily. All right. Hello, world. This is CS50. My name is David Malan, and it's so nice to see so many of you here today. If you're relatively new to Zoom, allow me to give you a quick verbal tour of what you can do while logged in here today. If you're on a laptop or desktop, odds are along the bottom of your screen, you'll see a few buttons, one of which is participants. If you click on participants right now, you'll see everyone else who's joined the room already. I'm seeing about 740 plus people on my own screen here. There should be a chat button along the bottom of your screen as well. If you click that, you're welcome to chat with each other throughout today's class. And indeed, if you want to answer each other's questions, please feel free to do so there or share URLs about related material. Brian and I won't really be able to keep an eye on the chat window because it'll fly by so fast, but there will be opportunities for questions and answers, which Brian will ultimately call on at the end of the day. We'll have as well the ability to unmute folks. Right now, everyone is muted by default, but if Brian calls on you, you'll see a prompt inviting you to disable mute and actually speak and answer to some question. So these are not office hours today. Those will be back next week. Today is an introduction to artificial intelligence and the world of machine learning. If you are unfamiliar with this world, you will no longer be in just a little bit. And if after today you'd like to learn more about artificial intelligence, do know that Brian teaches a class that's freely available on edX as well as via OpenCourseWare, the URL for which I've just pasted into the chat window. But without further ado, allow me to introduce today's teacher, CS50's own Brian Yu.
Thanks very much, David. So good to see you all here today, and looking forward to getting an opportunity to introduce to you all the world of artificial intelligence. So before we begin, I thought we'd start just by asking a question to you all. I'm curious among all of you, what are some examples of artificial intelligence that you have encountered or interacted with in your life, maybe recently? So examples of any kind of artificial intelligence, computers behaving intelligently. If you go into the Zoom participants window, you should see a raise hand button you can click on if you'd like to raise your hand to offer an answer. And let's see, I see a couple of hands are going up. And let's call on Tushar. Tushar, would you like to offer an answer for us? Examples of artificial intelligence.
Yes, sir. Hello.
We can hear you.
Yeah. So I want to tell about AI that examples like Alexa and Google also, because whenever we use Google, sir, then take the information from us. But if there is some error, then they practically processes that error, and then they give a required output. And many a times we also, whatever we get from that means what to say, that output from it is almost precisely correct.
Yeah, absolutely. So services like Alexa, where you can ask a question and get an answer, or you can give it a problem and it can potentially solve that problem for you. Definitely, that's one case where you might encounter artificial intelligence. What about another example? Artificial intelligence that you may have encountered in your everyday lives. Let's see. Let's call on Bilal, if you'd like to offer an answer. Bilal will need to unmute yourself first. Yeah, there you go.
Yeah, I guess thank you for this online class right now. But I guess one example for me in my personal life is that I'm an accountant, an auditor, and within my firm, essentially, the way we do our practice is that when we go to a client, we have a whole computerized checklist, and they have these specific tailoring questions at the start of the checklist. And depending on the tailoring questions that we answer, um, it spits out a customized list of procedures that we have to do depending on the um, checklist questions that we've answered. So it's basically, a little intelligent. I believe it's like a scripting program that someone's written with if-else statements. But I guess that's one example of artificial intelligence in my personal life.
Yeah, absolutely. And artificial intelligence is starting to show up in a lot of industries now as it's becoming more and more efficient for a computer to be able to solve certain types of problems that might be more challenging for a person to solve, for example. So we're going to take a look at a variety of different forms of artificial intelligence today. One example of artificial intelligence you might come across is something like playing a game, for example. So if you're familiar with tic-tac-toe, where the goal is to try and get 3 in a row, this might be a way where a computer could play this game pretty well, for example. So imagine, for instance, that you are playing X and you're trying to get 3 X's in a row, and you play in the middle, and your opponent, the O player, responds by maybe playing here on the top row in the middle there. And now it's your turn. It's your turn. You're trying to get 3 in a row. Where should you place the X if you're trying to win this game, if you're a human trying to strategically reason about how to play the game? And in fact, I'll go ahead and just poll all of you right now. So you should all see a poll that you can answer. So you're playing tic-tac-toe. You're trying to win. Where should X play? Should X play in the corner? Should X play on the edge? Or maybe both are equally good? So I'll give you a couple of seconds to respond to that and maybe think about how you would play this game strategically. And then we'll take a closer look at how it is that a computer might try to answer the same sorts of questions. So give you a couple more seconds to work on that. It looks like about half of you have responded to the poll question here on Zoom. All right, and we'll give you one more second. All right, let's go ahead now and close this poll. And we'll take a look at what the answers were. So let me go ahead now and show you all the results. And it looks like 355 of you said moving in the corner was the best place to go. 171 of you said either one is okay, and about 102 people said that you should go on the edge. And it just so turns out that there are potentially multiple ways to win this game, but probably the best strategy in this position, as most of you indicated, is to play in the corner. Reason being, if you play in the corner, O must block you, so O is going to play in the lower left, for example. And here, X has a very good move to play in a position where they have 2 possible ways of getting 3 in a row. They can get 3 in a row across, or they can get 3 in a row up and down. So no matter what O does, X is going to be able to find a way to block. So this is one example of artificial intelligence in game playing. You may have also encountered artificial intelligence with things like handwriting recognition. You can write something down, and artificial intelligence can figure out what the text of that particular message is. You might encounter AI in your email, for example. You have your inbox and you have your spam filter, and when a whole bunch of emails come in, your computer somehow figures out which emails are likely good emails and which emails are likely spam. Sometimes it makes a mistake, but for the most part, it does a pretty good job. You might see something similar when you're watching videos on YouTube or Netflix, for example, where you have watched some sort of videos, and YouTube is keeping track of which videos you've watched. And then YouTube is able to recommend videos to you, suggest videos that you might like to watch based on the videos that you've already watched. So AI can do some things that humans naturally think of as intelligent, but can also do some things that humans might not be so good at, like recommending which videos for you to watch, or even generating data too, which has been in the news in AI a lot in recent days. In fact, I'm going to now show you two pictures, image 1 on the left and image 2 on the right, both faces. And I'm going to ask you all a question. Which of these images is generated by a computer? That is to say, not a real person, but a fake person that the computer has generated. So I'll go ahead and launch this poll. You have image 1 on the left, image 2 on the right. Which of these two was generated by a computer? I'll go ahead and give you all an opportunity to answer that. Maybe take a couple more seconds. And all right, let's take a look at the results. And it seems like 63% of you or so thought that image 1 was generated by the computer. 37% of you thought image 2 was generated by the computer. It turns out you're both right. Both of these images are generated by a computer. Neither of these two pictures is a real person. It's just a computer that has been able to come up with an image that looks like a person. And we'll get a chance to explore today how that works as well. So all of this falls under the broader heading of artificial intelligence or decision-making more generally, where we would like for an AI to be able to come up with a good decision. And so let's start with a simple example of AI trying to make decisions. Maybe you've played a game like this before, where you're moving a little paddle along the bottom of the screen, and you're trying to bounce the ball in order to hit all of the blocks. Imagine you're playing this game, and you see the paddle move, or you see the ball move in this direction. And you're trying to program the AI playing this game to say, should the paddle move to the left, or should it move to the right, or should it not move at all? And I won't poll you, but if you're in the Zoom chat, just go ahead and write into the chat, would you move the paddle to the left or right, or don't move the paddle? And all right, it seems like people are saying yes. Everyone's saying yes, we should obviously move the paddle to the left. But what was the process? What questions did you ask in order to determine that was the right thing to do? Well, to answer that question, we can construct what we might call a decision tree, where we ask a question, and then we consider, based on what the possible answers are, what decision we could make. And in this case, our decision tree might look something like this. We ask a question, is the ball to the left of the paddle? If the answer is yes, then we move the paddle to the left. Otherwise, if the ball isn't to the left of the paddle, well, now we need to ask another question. We ask something like, is the ball to the right of the paddle? If the answer is yes, we move the paddle to the right. And otherwise, we don't move the paddle at all. So this is a decision tree that can play this game, that can play the paddle game in order to make sure to always hit the ball. So now, how would you apply this to a game like tic-tac-toe, for example? So I'll pose this question to all of you. If you'd like to raise your hand and offer a response. If you're playing tic-tac-toe, what goes into the decision tree? What questions do you ask if you want to try and calculate what the right move to make is? So we'll go ahead and see what you all think. Let's go ahead and see what, Ruth, if you'd like to offer an answer. If you're trying to write a program to play tic-tac-toe, what might be a question that you would ask?
A question that you could ask is maybe like where O is, so that we can like use that to try to find a better position for X to be.
Okay, great. So if O is playing and maybe O is close to getting 3 in a row, you might want to ask a question about, like, is O close to getting 3 in a row? And if so, you might want to block that, for example. What's another question that you might want to ask if you're playing this game, if you're trying to program a computer to be able to play tic-tac-toe and hopefully play it well? Hardik, why don't we go to you if you'd like to offer a question that you might want to ask?
Yeah, so if we can just program some cases, like if in this block X is there and in this block X is there, so the next X should go in this block, so there will be 3 X's in a row and X will win.
Yeah, great.
So,
if I have 2 X's in a row, then I can make the decision to like play the third X in order to get 3 in a row. After all, that's how you would win the game, for example. So that's what our decision tree might look like, for example. So if we might start by asking the question, can I get 3 in a row on this turn? If the answer to the question is yes, well, then let's play in the square to get 3 in a row. If the answer is no, then I might ask the question that Ruth asked, can my opponent get 3 in a row on the next turn? And if so, then we can block the opponent by playing in whatever square blocks them from getting 3 in a row. But if the answer is no, well, then we need some other decision procedure. We need other questions that we might ask. And this actually gets a little bit more complicated. You might be able to come up with questions to be able to answer that. But what we'd really like is to be able to train a computer to be able to solve these problems on their own. So we want to train a computer to be able to play the game without us, the humans, needing to teach the computer how to do so. And so we're going to take a look at how we can train a computer to make optimal decisions, how to make the best decision when playing a game. And the algorithm that we'll introduce is an algorithm called Minimax. And what the idea of Minimax is that computers might struggle to understand a game in general if you draw out lines on a paper in X's and O's. But computers, which are really just based on binary, are really good at understanding numbers. So if we can find a way to turn tic-tac-toe and turn that into numbers, well, then we can put it into a format where the computer is going to be pretty good at trying to solve these kinds of problems. So as far as the computer is concerned, we can take the tic-tac-toe game and divide it into 3 possible outcomes. Either O wins the game, which you see on the left, X wins the game, which you see on the right, or nobody wins the game, which you see in the middle. And what we're going to do is we're going to assign a numerical value or a score to each of these 3 possible outcomes. So O winning the game, for example, would be -1. X winning the game would be +1. And nobody winning the game, a tie, well, we'll just call that a score of 0. And now we have some sort of goal, some numerical goal that each player can follow. If you're the X player, your goal is to maximize the score, to make the score as big as possible. 1 is better than 0, 0 is better than -1. If you're the O player, we'll call you the minimizing player. Your goal is to minimize the score. For you, -1 is better than 0, and 0 is better than 1, because winning is better than tying, and tying is better than losing. And so what we'll try to do is, given any tic-tac-toe board, we'd like to give it a score, either -1 or 0 or 1. So this tic-tac-toe board, for example, where X has 3 in a row, right down the middle there, X has already won this game, so its value is 1, because X has won the game. If we take a look at this board, though, this game is not quite over, but let's assume it's X's turn to move. So X gets to decide where to go next. What score should this have? And based on this, well, if it's X's turn to move, if X makes the best possible move, X can play in the middle row and get 3 in a row horizontally. And so this also has a value of 1, because X is going to win this game. And so let's now give you a slightly more challenging problem. Let's take a look at this game board right now. And let's say it's O's turn to move. So O is trying to get 3 in a row. X is trying to get 3 in a row. O is trying to stop X from getting 3 in a row, and vice versa. The question that I'm going to pose to you all now is, what is the value of this particular game board? And so what is the value of this game board? You should see a poll appear now. -1 means that O is going to win the game if both players play the best move. 1 means X is going to win the game if both players play the best move. And 0 means it's going to be a tie if both players play the best move. So what is the value of the board? What score should we give to this particular tic-tac-toe board? It looks like about half of you have responded to the question. It's okay if you don't know. Go ahead and just make your best guess, and then we'll take a closer look. And all right, let's go ahead and see the results. It looks like 81% of you said it's going to be a tie if both players play the best move. About 4% of you said O will win, and about 14% of you said X is going to win. And it looks like the vast majority of you were correct. If both players play correctly, the game is going to be a tie. And would someone like to explain why? Would someone like to explain why it is? Go ahead and raise your hand if you'd like to offer an answer. Why it is that the game is going to be a tie if both players play the best moves. And let's see whose hand's raised. Let's go to Arnav, if you'd like to explain why. I know you can't see the board right now, but if you'd like to offer what you remember at least.
So if both O and X play their best move, then O will usually put the circle in front of the X where it is making 3 in a row. So the next move of X is going to be the left on the corner one. So that's why it's going to be a tie.
Great answer. And what you've effectively done is what the Minimax algorithm is going to do too. In order to determine the value of this board, you consider where could O go? And O really has two possible places where O could move. O could either play in the top left, or O could play in the bottom. And if O plays in the top left, well, what's going to happen then? Well, in that case, X is going to play in the bottom, and X is going to get 3 in a row and win the game. When X wins, that has a value of 1. And so if that has a value of 1, then we consider, well, what's the other possibility? X doesn't have to play in the top left, or O doesn't have to play in the top left. O could also play in the bottom here, in which case X only has 1 square where they can play in, and this game is a tie. It has a value of 0 because nobody has won this game. X doesn't have 3 in a row, and O doesn't have 3 in a row. So what you see here is a branching point. O has 2 choices, one of which leads to a value of 1, meaning X wins the game, and the other has a value of 0, meaning the game is tied. And if O is the minimizing player, they're trying to make the value as small as possible, and they have a choice between a value of 1 and a value of 0. Well, 0 is smaller than 1, so we can say that this board also has a value of 0. If they both play their best moves, the game is going to be a tie. And this is how the game of tic-tac-toe can be solved by an AI, by just considering all of the possible moves and mapping out what's going to happen. If you look one move further, you might imagine an even bigger tree structure like this for calculating more and more complex variations and possibilities in what might happen in this particular game in order to determine what the value of any given game board happens to be. So the code for this, if you were going to try and write this in code as an algorithm, is going to look a little something like this. To play tic-tac-toe, you might start by saying, if the player is X, asking a question, a sort of condition, we'll then look at all the possible moves and calculate what the score is for each of those possible moves. And then based on all of those possibilities, you'll just choose the move with the highest score. You'll choose the best move that's available to you. Otherwise, if the player is O, you'll do the same thing. For all the possible moves, you'll calculate the score for each board. But if you're the O player, instead of choosing the move with the highest score, you'll instead want to choose the move with the lowest score in order to try to win the game. So Minimax says if you're the X player, pick the move that makes the score as big as possible. And if you're the O player, pick a move that makes the board as small, makes the score as small as possible. And so that then is how we might play a game like tic-tac-toe in order to be able to end up with a solution that allows the AI to play this game very, very well. And there are variations and variants on this algorithm too that can help to solve these sorts of problems. So now what I think we'll do is move on to a slightly different type of problem in artificial intelligence. Game playing is one kind of AI, and we've scratched the surface of what those algorithms might look like. But what I want to talk about now are what we call search problems. And search problems are a very common type of problem in artificial intelligence anytime we're trying to look for the solution to a problem. So this might come up in the context of a maze, for example, where you're trying to get from one point to some other point by following along without running into any walls, for example. And you might imagine this in real life if you imagine trying to write an algorithm for driving directions, like Google Maps, for instance, where you're trying to figure out what is the best way to get from one point on the map to another point on the map. We'd like for our AI to be able to solve these kinds of problems, to find a way to get from one point to another point. So let's take a look at an example. Here's sort of a digital map. We are trying to get from point A to point B. And these grayed out squares you can think of as walls. We can't pass through those walls or obstacles, but we would like to find a way to get from A to B. And I'll pose this question to all of you now, actually. Let's go ahead and ask you all, if you were trying to write an AI to be able to find a way to get from A to B, what sort of algorithm might you use? What sort of logic might you use if you were trying to write a program that could figure out how to get you from one point to another point? So let's go ahead and call on someone. Let's see whose hands are raised. And let's ask Makarand, if you'd like to offer your thoughts on how you would write a program to get from one point in a map to another point.
So I would see whether the adjacent square is grayed out or not. And if it is not grayed, I will move to the next point and go on looking to adjacent square until I get to B.
Yeah, great. So you basically go, and if you see a wall, you know you can't move in that direction. So you look for directions where there's open space for you to go. Absolutely a perfectly reasonable strategy for trying to solve this kind of problem. And so we could come up with an algorithm that does just that. And the algorithm that we'll look at first is one called depth first search. And the idea of depth first search is exactly what Malan was just saying. Basically, look around you. If you see walls, you know you can't go in that direction. But if you see open space, we'll just try that and see where it takes you. So the way this algorithm might work, if I'm starting at A, is I say, okay, well, right now, the only direction I can go is I can go to the right. So we can explore that way, keep going, keep going, keep going, keep going. Now I've suddenly reached a fork in the road. I could go left or I could go right. Right now, our AI doesn't really know which way is better. So the AI can just say, let's try one and see what happens. We can try going to the left and just keep going, keep going. All right, we've hit another fork in the road. I can go left or right. I don't know which one is the right way to go. So the AI just picks one. And maybe we're going to go left this time. Now suddenly we've hit a dead end. It doesn't seem like there's any way for us to make any kind of progress here, going in this direction at least. So we need to do something else. And what we can do in this case is just back up. Go back to the last point where we made a decision and say, okay, we tried going left. Now let's try going right. So we're going to go to the right. We hit another dead end. So we back up. And now we try, okay, let's try this path. And effectively what depth first search, otherwise known as DFS, is going to do is it's going to keep trying paths. And every time it hits a dead end, it's going to back up and it's going to try another path in order to eventually get to the destination. So this then is depth first search, which finds a way for us to get from A to B. And it will, if there is a way to get from A to B, it will be able to find a way to get us to that point. But if you're trying to get driving directions, for example, you probably care not just about getting from A to B, but finding the fastest way to get from A to B, the shortest path, in other words, to get from A to B. So I'll pose this question to you all. How good is this algorithm, depth first search, at finding the shortest path? In other words, will depth first search find the shortest way to get from point A to get to point B? So maybe it always will find the shortest path, maybe it never will find the shortest path, and maybe it sometimes will. So go ahead and take a moment and answer that question. Will depth first search find the shortest way to get from point A to point B? Always, sometimes, or never? Looks like most people have answered. We'll give you a couple more seconds to answer the question. All right, and let's take a look at the results. It looks like 82% of people said that depth first search will sometimes find the shortest path from A to B. And it turns out that's correct. For those of you who said always, it's true that there are some cases, like the case we just looked at, where depth first search will find the shortest path. And for those of you who said never, there are definitely some times where depth first search will not find the shortest path. And would anyone like to offer an explanation as to why? So maybe either if you said sometimes, or maybe if you said something else, and now you have a different idea, if you'd like to raise your hand to offer your reasoning as to why depth first search will only sometimes, but not always, find the shortest way to get from point A to point B. Let's call on someone, and let's call on Isha, if you'd like to offer an answer.
Hello, I would like to say that depth first search is, you can say, is not able to find the shortest path when the distance is large. You know, when the distance is short, I think the breadth first search is more for long. For example, depth first search is useful if it is for short distances. For long distances, I think that breadth first search is more useful.
Yeah, so there might be cases where if the goal is really far away, you might end up having to, you might try one path and it doesn't work and you go really far and you hit a dead end and then you try another one. And it might be a while before you're eventually able to find your way to whatever the goal might be. And I'll show you an example of that now, of where that might come about. If you imagine this map that we're looking at here, where the goal is to get from point A to point B, and you're following depth first search, you have two options. From point A, you can go up or you can go to the right. And whenever depth first search has two choices, it just picks one and tries it. So from point A, you might move, hit a dead end, or maybe not hit a dead end, and eventually find a path to get from A to B. And this is a path. It is a way to get from point A to point B, but it's not the best way, because while this does get us to the destination, there's a shorter path, which if you were looking at this, you might be able to see as well. And just by luck, we happen to not explore that shorter path. And so what Isha was suggesting is another algorithm that we can use that maybe will be better at trying to find these sorts of shortest paths. And this algorithm is called breadth first search, or BFS for short. And the difference now is that whereas in depth first search, whenever we hit a fork in the road, we just picked one until we hit a dead end. In breadth first search, when we hit a fork in the road, we try going in both directions, and we just alternate between going left and going right, back and forth, and seeing if that gets us anywhere too. So the way this might work is that if we're at point A and we can go up or to the right, rather than pick one and try it, we pick both. We first go one step up, and then we check to the right. And then we check another step up, and then we check another step to the right. And we just alternate going back and forth, slowly expanding away from our starting point until eventually we're able to find a way to get to point B. And this ends up being the shortest way to go because we always take one step at a time, one step at a time. We'll always find the shorter paths before we find the longer paths that are going to take longer to get to. So Isha was absolutely correct that if we're really looking for the shortest way to get from A to B, this might be a better way to do just that. But even breadth first search isn't perfect. There are still some drawbacks we might run into. In fact, if we go back to this original maze, for example, if we're trying to find a way to get from A to B, let's look at what might happen if we use the breadth first search algorithm. We go, go, go. When we hit a fork in the road, we try going in both directions. I say, all right, let's go to the left and let's go to the right. Let's go to the left and to the right, so on and so forth. And we keep trying. Every time we hit a fork in the road, like right here, we can go to the right or we can go down, and breadth first search is going to say try both. Go to the right and then go down, go to the right and then go down. Every time there's a fork, we're going to try both of those possible options until we eventually find our way to get from A to B. And that did work. We found the shortest way to get from A to B, but it took a long time. We explored a whole lot of paths that we probably didn't need to explore because they didn't really lead anywhere. But we didn't know they didn't lead anywhere until we sort of tried them out. So how might we improve on this algorithm? How might we make it so that we can find our way to get to the destination without needing to explore as much, to do so a little bit more efficiently? If you'd like to offer an answer, go ahead and raise your hand as to how we might make this algorithm a little bit more efficient. And let's call on A99B is your username on Zoom, if you'd like to offer your answer.
Hello. Yeah, what about heuristics, for example? So
yeah, great. And what's a heuristic? What does that mean?
Deciding based, for example, on a distance to a goal.
Yeah, sure. Something like distance. Something to say, if we have two places we can explore and one of them looks closer to the goal, maybe that's the one to explore first, for example. So let's go ahead and take a look at what that might look like. It's a very good answer. So what we'd like to be able to do is to say that when we hit a fork in the road, something like this point, and we could go A to the left or B to the right, and we're trying to choose between whether to go left or trying to go to the right, we can more intelligently say that, you know what, going to the right is probably the better choice. It looks closer to the goal, and so that's probably the better way to go. And so we can try and formalize this idea too. We can say something like, we want to find some way to represent numerically how we can find a better solution. And so this is the difference between what we call uninformed search, which is sort of just blindly searching by trying different paths, and informed search, where we can be a little bit more intelligent about how we're trying to go about the search process. We're using knowledge about the problem to find a solution more efficiently. And so to do so, we're going to use a heuristic. And that heuristic might look something like this. If we're trying to choose between C and D and answer the question, is C a better place to be if we're trying to get to the goal, to the green B, or is D a better place to be? Is that a better place to be? Which is better, C or D? Go ahead and just paste it into the chat if you're here on Zoom. Would we rather be at C or would we rather be at D? And all right, looks like everyone is saying we'd rather be at D, but how do we know? How could we tell a computer to do that? Well, there are a number of ways we can do that, but one way is what's called the Manhattan distance. And the Manhattan distance is a rule that says to figure out which one is closer, just count how many squares like up and to the right would you need to go to get to the destination. And based on just drawing these straight lines, ignoring the walls, just drawing straight lines, we can see that D looks like it's fewer squares away from B than C is. So D is a better place to be than C. And in fact, we could number all of the squares in this grid based on how far away they are from the goal. So for example, this square right here, that one's only 1 square away from the goal, whereas this square is 2 away from the goal. And so you could count, just based on this Manhattan distance heuristic, how many squares you would have to move in order to make it to that ultimate goal. And so now what our algorithm is going to do, an algorithm called greedy best first search, is whenever it hits a fork in the road, it's going to pick the smaller number, the number that looks like it's closest to that goal. So we might start with going, okay, we'll go ahead and make our moves. And when we hit the first fork in the road, we can go left or we can go to the right. Going left will result in us being 13 squares away from the goal. Going to the right, we're only 11 away from the goal, according to this heuristic. So going to the right looks like it's probably better. So we'll go to the right and we'll try that instead. Here we can go up or to the right. Both look equally good because in order to get to B, we do have to go up, but we also have to go to the right. So we can just try one. And if we hit a dead end, we can try something else. We can try here. Here we have 2 options. Going to the right and we'll be 6 away from our goal. Going down and we'll be 8 away from the goal. So 6 is a better place to be. It's smaller than 8. So we'll go ahead and take that route. Here we can go up and be 4 away, or we can go down and be 6 away. And here, even though it might not be the best choice, 4 is going to be what the AI chooses. It looks like going up is the better way to go. So we'll go up, and when we hit a dead end, well, then we can try something else. We can try going around until we find our way to the goal. So what this algorithm does is it always just picks the smaller number whenever it has these sorts of choices. And it turns out there are improvements upon this algorithm too, that artificial intelligence researchers have been able to come up with to find better and better, more efficient, more effective ways of trying to find a way to get from one point to another point. So these are some examples then of how you might write an AI to be able to solve search problems. Another type of AI that we'll go ahead and take a look at next is something called reinforcement learning. And the idea of reinforcement learning is that our AI is going to learn from experiences. It's going to try something, and if it doesn't work, it tries something else. So to set the scene, for example, let's imagine that we are this yellow AI living inside this grid, and we're trying to get to the green goal on another square in this grid. But there are obstacles in the way, sort of in this world that we don't want to crash into, but the AI doesn't know where those obstacles are. The obstacles here described in red. And so what our algorithm could do is we could say, all right, right now we don't know where to go. Let's just try something. And if we run into an obstacle, well, then we learn not to do that in the future. So we try something else. We say, all right, let's try going this way. That didn't work either. And so we try something else. We keep trying random things until we make our way to the goal. We'll try something else. And if that doesn't work, we keep trying again and again and again. And every time we fail, we learn what not to do the next time. And eventually, if you do this long enough, you end up finding a good path, a path that does get you from the starting point to the goal. And so here our AI little robot is able to navigate its way through this world, finding its way to the goal. But this algorithm still isn't great. It's been okay. We've been able to avoid the obstacles. But, and I'll go ahead and pose this question to all of you. So if you'd like to raise your hand to answer it, what's one problem with this algorithm that we've just seen here where the AI is trying to find its way to get to the goal? Let's call on someone and see who might be able to offer an answer. Let's see whose hands are raised. Let's see what Carlos thinks. Carlos, where are you from, and what do you think we could do to make this algorithm better, or what's a problem with the algorithm?
Hi, I'm from Mexico, and the problem I think that is that once it finds a path, it it keeps that path in mind that it's the best path, but it is not necessarily the best path. So
yeah, great. Absolutely correct, Carlos. So we have an AI that anytime it does something wrong, it learns what not to do. And anytime it gets to the goal, it learns to do that. And so it's learned to do something, even if it might not be the best way to do that. Even if there might be a faster, shorter path to get to the goal. And I'll go ahead and ask another question. How might we fix this problem? How could we modify the algorithm so that it might find a good path, but it can also try and hopefully find an even better way to avoid the obstacles too? Possible ways we can improve upon this. Yeah, Judy, where are you from and what do you think?
I'm from Egypt, and I think that maybe we could find an algorithm to add to it to maybe tell the AI to continue searching until we find another one that is shorter than the path we've already found.
Yeah, great. We need something to add to the algorithm to say, even if you've already found a path, keep exploring things that you haven't necessarily explored before, because maybe you'll find a better path after that. Absolutely correct, both Carlos and Judy. And so what we might want to do here is to say, rather than following, we want to try and find this sort of better path that we didn't find originally. And so here we have a tension between what we call an AI exploring and exploiting, where exploiting means taking advantage of information we already know. We already know how to get to the goal, versus exploring, which is looking at things that might be unfamiliar. Maybe trying something because maybe it'll lead to a better solution, but maybe it won't. And so here's one approach to how we might write an algorithm to balance exploring and exploiting. And to write a little bit of pseudocode here, we have a value called epsilon that represents what % of the time we're going to make an exploring choice, a random choice. And so here we're saying 10% of the time, let's just explore randomly. And so here we can write some code that says that if we generate a random number and it's less than epsilon, which happens 10% of the time, then make a random move. So 10% of the time, don't use the information we already have, just explore. And the other % of the time, 90% of the time, make the move with the highest value, the best move we know of so far. So an algorithm like this, most of the time, will make moves that it knows are good, that it knows are smart moves. But occasionally, 10% of the time, it tries something random, so that, as Judy said, we can hopefully find a better way to get to the goal, even after we've already found a way. And so just to give a brief demonstration of this, here's a robot that used an algorithm like this to learn how to flip pancakes. So first, a human demonstrates the task. It shows the AI, the robot, what flipping a pancake even means. And so here the human is flipping the pancake for the AI, demonstrating it a couple of times. And then we let the AI try it on its own. Here's its first try on flipping a pancake. Okay, it didn't do so well, so it can try again. This is after 3 tries now, trying to flip a pancake. Okay, still not great. After 5 tries. So every time it's trying, it's starting to learn from its experiences. It learns what not to do. It learns what types of motions don't result in successfully flipping a pancake. And over time, this algorithm can start to get better and better. And so what you'll see here is now after 15 tries, it looks a little bit closer, maybe, though still not great. Reinforcement learning can sometimes take quite a bit of time. And this is why oftentimes you need high power computers with a lot of computing power to be able to solve some of these really tough problems. But now as you're taking a look at the AI, it seems quite a bit better, that after trying this again and again, evaluating itself by looking at how it's performing every single time, it's eventually able to learn this kind of behavior. It's able to learn how to flip a pancake, for example. So we'll take a look at a couple other types of algorithms. Let's take a look now at genetic algorithms, which are an algorithm based a little bit on humans and how, or based on organisms and populations and how they work and how genetics and evolution works. And the idea of a genetic algorithm is to say, we're going to start, if we're trying to solve a problem, by making a whole bunch of candidate programs randomly. We create a whole bunch of random AIs, and we let them all just repeat this process. So we've created a whole bunch of random AIs, and for each one of them, we calculate its fitness. In other words, how good is that AI? And then what we do is we remove the least fit candidates. So whichever AIs didn't perform very well, we get rid of them. and then we duplicate the ones that did do well, making some small changes randomly again, and seeing if this next generation does better. So the idea here is that one generation after another, we remove the worst performing AIs and just let the best performing AIs continue to duplicate themselves. And so here's an example of this with a simulation of some self-driving cars, for example. Each of these rectangles that you see is a simulated self-driving car. The little X's, the crosshairs, are the car's sensors where it's looking at what's around it. And we now are trying to train these cars to drive. And initially in these early generations, they're not doing a very good job. They're crashing into walls all over the place. But over time, every generation, and you can see the generation counter in the lower left, these AIs are starting to get a little bit better. They're starting to, by removing the cars that don't make it very far and duplicating the cars that make it further, we're able to repeat this process again and again, getting cars that can move closer and closer to their destination. And so we're looking one generation after another, and that car, as you're looking right now, did a pretty good job compared to those early generations that really didn't move very far at all. So that then is what a genetic algorithm might look like. And there are lots of contexts where genetic algorithms can come about. So one example might be in terms of video recommendations, for example, where where a website like YouTube is trying to recommend videos to you. And what it can do is it can try a whole bunch of different recommending AIs, and it can check which of those AIs are doing a better job, which AIs are better able to predict what video you might want to watch. So it can get rid of the AIs that don't do a good job and duplicate the AIs that are doing a good job, so that generation after generation, these AIs are able to get better and better and better. So this then is just one example of AIs that are able to model themselves after something in nature. Here, modeling themselves after evolution, where generation after generation, the AIs get better and better and better. But AI researchers, especially in recent years, have taken this a step further and have started to think about how can we try and better solve problems that humans are good at solving by structuring our computers the way human brains are structured. So human brains are composed of neurons, one of which is a diagram you see here. And these neurons are connected to each other. So neurons pass information from one neuron to another neuron inside of what we might call a neural network. And so what a lot of AI researchers have done recently is creating what are known as artificial neural networks, where we create these networks, except instead of using real biological neurons, we just use what we call units, which you can think of as just something inside of your computer, some value that is being stored inside of your computer. And these units of an artificial neural network are connected to each other. So each unit represents some value stored inside the network, something stored inside of the computer's brain. And this arrow represents some sort of function that takes the unit on the left and calculates some value for the unit on the right. So some way of transforming inputs to outputs. So this is a fairly simple network that connects one input value to one output value. But you could imagine bigger networks like this one that connects two input values to a single output value, or even something larger than this. Here's a big network that connects 3 input values through a whole bunch of units in between to get to an output value. But the idea of all of this is that what a neural network really is it is some function that takes input data and turns it into output data. And if you have a lot of example data, what we call training data, a lot of sample inputs and sample outputs, well, then you can do a little bit of learning. You can learn how you transform the input to the output. You can learn what those connections inside of the neural network can be. And there are so many applications of this technology for things like handwriting recognition, for example. You might, if you give the computer a whole bunch of sample handwritten digits and what digit they are, the computer can be trained to learn how to map the image of a handwritten digit, like the number 8, for example, to the actual number 8. And by giving the computer enough data, it can begin to learn the function that transforms this input into that output. Or likewise, for something like detecting spam email, you might give the computer a whole bunch of email, some of which you tell the computer this is good email, and others of which you tell the computer this is spam email. And the computer learns a way to transform that input, the email, into a category for it. Is it spam or is it not spam? And these types of neural networks have been incredibly powerful for doing all sorts of things that humans can do, and even things that humans can't do. So you remember from earlier this session, we were talking about these two people, which again, aren't real people. Both of these people were generated by a computer. They're not real. But how did that happen? Well, it's just a mapping of inputs to outputs based on training data. And the way this actually worked is that by starting with like a 4x4 grid of pixels here that doesn't look like a person at all, you train a neural network to say, how do I take this 4x4 grid and turn it into something that looks a little bit more like a person, maybe an 8x8 image that here you can kind of start to see the face and the hair and the shirt, for example. And then you can repeat the process again. Learn a way to take this image and add a little bit more detail to that. And by giving the computer lots of training data of real people and what their faces look like, the AI can slowly learn how to add artificial detail into the image until you get something that really looks quite like a real person, to the point where it's almost indistinguishable whether it's real or not. And it's all about this mapping, this translation of inputs, like this 4x4 grid, to an output. By giving the computer access to this sort of data, we're able to make this sort of transformation. And so these are just a couple of the examples of the power of these artificial neural networks and what it is that they can do. So just to wrap up, if this kind of thing is interesting to you, as David mentioned earlier, I'd encourage you to take a look at this class that I teach, CS50's Introduction to Artificial Intelligence with Python, that will teach you a lot of these principles we've talked about today, go into even more depth and cover even more topics in the world of AI. And along the way, you'll have the opportunity to write Python programs to build AI of your very own. So you'll build an AI that uses the Minimax algorithm to write a program that is able to never lose at a game of tic-tac-toe, for example. You'll build AIs that are able to logically reason and solve problems, to be able to play a game like Minesweeper, figuring out where all the mines are, and you'll write an AI in Python to do just this. You'll build industry algorithms and applications, like implementing an AI kind of like the one Google uses to rank pages in Google search results to figure out which results are more important than other pages. You'll write AIs to do things like generating crossword puzzles, and we'll even take a delve into the world of things like self-driving cars, writing an AI that can look at street signs and tell them apart, figuring out what one kind of street sign looks like versus another, and building an AI that can classify these sort of street signs into each other. So if this kind of thing is interesting to you, if you enjoyed today, that's the URL again that you're looking at here to go to that class to explore all of these topics in artificial intelligence and even a little bit more. And so thank you all very much. Before we wrap up, I'll turn things over to David to do a bit of closing remarks and to take a group photo. But thank you so much for listening today.
Indeed. Thanks so much to Brian for leading today's class. As you may know from past classes, we have a tradition of doing a group photo. If folks are comfortable, please turn your cameras on. If they're not on already, if you'd like to opt out, simply turn your camera off. And now we just have to start smiling and waving as CS50's team behind the scenes takes a whole bunch of screenshots, because there's still 775 of us now in the room. And so it's going to take a few clicks on behalf of CS50's team to go from the left to the right, taking one screenshot after another. And the team's really good with Photoshop. So later today, we'll take all of these screenshots and create a whole mosaic out of them so that we all appear to be on one huge screen all together. As we finish waving and smiling here for the camera, allow me to invite you to next week's office hours. We'll be joined by a special guest, CS50's own Doug Lloyd, who leads, as you may know, a lot of CS50's shorts. We will follow up with an email and an invitation with the day and time for that next week via which you can register. Well, I think I have stalled long enough with the hand waving and smiling. Thank you so much to everyone for participating. Please do keep in touch, and we hope to see you next time.
Thanks, everyone. Great to see you all.